Hello! In this video, we are going to prove the following theorem. Suppose G is a group, then the center of G is a subgroup of G. Now first, since G is a group, this means that G is equipped with a binary operation. G is closed under that binary operation. Associativity holds. G has an identity element, and every element of G has an inverse. Now, the center of G is the set of elements in G that commute with every element of G. In other words, the center of G is the set of elements G in G with the property that xg is equal to gx for all x in G. Now, to prove that the center of G is a subgroup of G, we are going to use the one-step subgroup test, which tells us the following. Let G be a group, and let H be a non-empty subset of G. Suppose for all A and B in H, A times the inverse of B is an element of H. Then H is a subgroup of G. Now, in proving this theorem, we are also going to be using some facts about groups, and those are as follows. Given any two group elements A and B, we have that the inverse of AB is equal to the inverse of B times the inverse of A, and given any group element A, the inverse of A is equal to A. Okay, so now let's get into proving this theorem. Now, to start the proof, let's first let G be a group with identity element E. And from here, we're going to show that the center of G is a subgroup of G. And to show that, we are going to apply the one-step subgroup test. So, to start out, let's first show that the center of G is non-empty, because that's a requirement for the test. Now, to show that the center of G is non-empty, we are going to show that the identity element belongs to the center of G. And to show that the identity element belongs to the center of G, let's take G to be E. In that case, we want to verify that this is true. Now, we know that the identity element of G is an element of G, so we're good here. So now we want to verify this condition. And to prove this condition, let's consider an arbitrary element of G, called x. From here, we want to show that xe is equal to ex. Now, by definition of the identity element, we know that xe is equal to x, and x is equal to ex. And therefore, xe is equal to ex. So, we see if x is any element of G, then xe is equal to ex. So, we have verified that this is true. And so the identity element satisfies all the properties to be an element of the center of G. And therefore, the identity is an element of the center of G, so the center of G is non-empty. So now we want to verify that this condition is true for the center of G. And to prove that, let's give ourselves two arbitrary elements, A and B, which belong to the center of G. Now, since A and B belong to the center of G, this means that A and B commute with every element of G. Now, the whole goal is to show that A times the inverse of B is an element of the center of G. And to show that, let's take G to be A times the inverse of B. In that case, we want to verify that these are true. Well, we know that A times the inverse of B is an element of G, so all that's left to verify is that this statement is true. And since we're trying to prove a statement about every element in G, well, let's give ourselves an arbitrary element of G, called x. From here, we want to show that this equality is true. So let's start out by writing the left-hand side. Now, since associativity holds, we know we can move the parentheses around xa. And then, since A commutes with every element of G, then in particular, A must commute with X. So we can flip these around. And then, applying associativity again, we can move these parentheses around X times the inverse of B. And then, applying this rule, we're going to replace x with the inverse of x. And now we're in a position to apply this first fact. In that case, we're going to take a to be b, and we're going to take b to be the inverse of x. With these substitutions, this becomes this. So really, this guy is equal to the inverse of bx inverse. And then, since b commutes with every element of G, that means b must commute with the inverse of x. So we can swap these guys. But now we're going to apply this property again. But in this case, we're going to take a to be the inverse of x, and we're going to take b to be b. With these two choices, this becomes this. So really, we can replace this guy with this. But again, we know that x inverse inverse is equal to x. And then, by associativity, we can move these parentheses around AB inverse. So, this chain of equalities shows that these guys are equal. And we have shown that these guys are equal for an arbitrary element x and g. And therefore, we have shown that this is true for all x and g. So, we have verified this condition. And therefore, AB inverse satisfies all the requirements to be an element of the center of G. And therefore, AB inverse is an element of the center of G. And so now, by the one-step subgroup test, we can conclude that the center of G is a subgroup of G. And so this completes the proof. And so yeah, that's pretty much it for this video.